Well, here we are. It's the physics video lecture. Physics 4B video lecture 1. My name is Carl Rundy, and I sent the syllabus out to everybody. So the first thing we'll do is go through the syllabus and then we'll start talking physics. Okay, so we have me here, Carl Rundy, and my email, KRUNDE at csufresno.edu. So this is what you send all your inquiries to, this email. We are not using Zoom and we're not using Canvas for the time being. I'll fill you in on that a little bit later, but for now, all communication to my email. And let's get started with this syllabus. You'll notice I kept it to a minimum. It's just one page. And let's see what we need to know here. Office hours by email, so that's been given here. Class Monday, Wednesday, 3:30 to 4:45 p.m. 2 video lectures per week, available at this YouTube channel. Homework assignments are announced in the videos, okay? So of course you can watch the videos pretty much anytime, but the reason we're synchronous is because I'm going to use class time for doing quizzes, okay? Quizzes and say the final exam as well. Good. So schedule numbers there, virtual synchronous. Classroom is there. Text, physics for scientists and engineers, Tipler, 6th edition. That's this brick. I've got this entire hard copy right here. And course material, chapters 17 to 30. We're starting with thermal physics. That's why I have some thermal physics demos here on the table. And then we'll be going on through electricity and magnetism. Now, here's where it gets important. Homework, pictures of your handwritten lecture notes and worked homework problems sent to me by email every Friday evening, no later than 6 o'clock p.m. So the handwritten lecture notes are a very important part of the class. That's how we just maintain a current status in the class, and our goal is to have really good lecture notes. So I encourage you to use plenty of paper, space everything out, then you have room to come back and fill things in. So that's a major project, is to produce some really nice notes, and then you take pictures of them once a week and email me those pictures. So there are 2 emails. There's an email for the notes, and there's an email for the homework problems, and you send them both to me every Friday before 6 p.m. So you send the emails to this address, and you always open a new message with the subject line. So new message, new email message every time. So that is for both of these emails. And then the subject line will be your name. Here, let's write that properly. I'm about to write my own name. Your name, Physics 4B notes. Okay. And then the second one is also your name, Physics 4B homework. Okay, so 2 separate emails, new message for each one. And then I will just check that you did it. For both of these, really, I'm just going to check that you did the work. In particular, these we want to have them look really good. So if you turn in your notes, you get a point each time, but if they're really good, you get a full point, and if they're mediocre, maybe you get 0.7 point, 0.7 points or something like that. notes, homework. Same with the homework, I'm just checking that you did it, I'm not grading it. So you want to do a good job though, because it's these homework problems that allow you to solve the test questions. As far as the homework goes, then the following week I will answer any questions. So I'll give you feedback on the homework by working homework problems here on the board for you. So send in your requests for certain problems you wanted to see worked, and I'll do them on the board. So that'll be the homework feedback. Otherwise, if you turn in neat looking homework, reasonably complete, then you just get the full credit for the homework. Okay, so there we are. The notes, really, we want them to, you know, when you're done, those notes should be a nice book and a record of all that you've done and learned. Okay. So after the homework, we have examinations. And what I'm doing for the examinations, it says here, daily quizzes at the end of each scheduled hour will begin in late February or early March. So we're going to do 4 or 5 weeks with no quiz, but then we'll start doing these between 10 and 15 minute quizzes at the end of each hour, which means at 4:30. Say at 4:30, I will schedule quizzes. At that point, they will be on Canvas, and they'll be timed, and Canvas generates random numbers, so everybody gets their own set of numbers, and we do a problem. It's just a single problem generally. And you know, we start about a month from now, and we get a good 15, 16 quizzes, 17 quizzes in the course of the semester. And then the final exam will just be a double quiz, half hour, 2 problems, and that'll be it. Okay, so what I say here, the final exam is just another quiz. It could even be just a single quiz as with these others. So yeah, that's how the exams are going to be, and I did this last semester with Physics 2A, and it seems to have worked pretty well. Okay, so we'll, we have a lead time of about a month, and then I just start doing these quizzes, and I can give you good hints on what's going to be on the quiz, so all that stuff can be worked out nicely. Worked pretty well last semester. What else do we have here? The grading, we're going to put 15% lecture notes, 50% homework, quizzes 70%. So you want to get all of these 15 plus 15 points. You know, if you diligently do your notes and your homework, you'll be able to get all of those points. Okay. Quizzes 70%, and we're just adding them up. Then I have a grade scale, very standard, 90 to 100 an A, etc. Question always comes up about curving it, and the answer is at the end of the semester, when all of the points are in, I'll make decisions on how to extend these ranges. So this here that you have on the syllabus, that's guaranteed, but it can only get better. I can only do things more in your favor. So yeah, but that can only be done, any curving of this grade scale, when all of the points are in, or when they're all, almost all in. Possibly before the final I can make a decision, but so that's nothing you have to worry about. Right now we're just going to get started and learn as much physics as we can. Okay, and I think that covers it for now. You have questions, you can always just email, and I'll be getting a lot of emails, but I'm not ignoring any. If for some reason I don't answer an email, just fire off another one, okay? And that, like I said, that seems to have worked pretty well last semester. So we should just have full confidence right now that we're going to make everything work out well. So that's probably enough for starters. I'm going to give a lecture. I've got some demonstrations here. I'll then give a homework assignment out of the text. And we'll see how far we get on that. You'll take these notes. Yes, so we have Monday and Wednesday lectures, so all the notes from Monday and Wednesday and all the homework assigned from Monday and Wednesday gets turned in these 2 emails every Friday. So that should work out pretty nicely. Okay, so let's get started on the material. Physics 4B, this is thermal physics and electricity and magnetism. I think I'll clear some board and just get a progression of ideas going here. Okay, thermal physics. So we're in chapter 17, and we're also going to go to chapter 20 because that's the order in which I like to present some of these ideas. Okay, so we're doing thermal physics. Now let me go ahead and put down something here. You've studied mechanics last semester all the way through waves. So when we have mechanics, we're dealing with kilograms, meters, and seconds, right? We have Newton's law, kilograms. So just in honor of Newton's law, mass times the second derivative of position is equal to our net force. It's a vector law. And we can also do this for point systems, in which case we'd have a subscript on each of these, okay? But yeah, we have mass, we have acceleration, we have force, and we have kilograms, meters, seconds. So this mass is kilograms, but here when I'm talking this M is meters, right? So everything in mechanics could be reduced to kilograms, meters, and seconds. And now we're going to go, here's one, into thermal physics, which seems to be something completely different. The way I want to introduce it is just to talk about sensation of hot and cold. So thermal phenomena, we're going to start really simple, hot and cold. Sensation. Right. So at that point we have no connection to mechanics yet. So we get the hot and cold sensation. I didn't bring the ice along, but I did bring the flame. So we've got a torch here. Okay, there's no coolant, it's definitely hot. And of course if you have ice in your hand, you feel the cold sensation. So that's where we begin. The phenomenon of hot and cold. The next one, we have here, dot, dot, dot. Then what's next? So what's next is another thermal phenomenon of expansion and contraction. So let me go ahead and write that out. Then expansion and contraction. And this is why I'm jumping into chapter 20, because I want to talk about this in a certain order. So thermal expansion. And the demonstration we always like to show, we like to show a couple of them. We have these balls and rings that are very closely machined. So here the ball will pass just through the ring. If you're looking at this closely, you wouldn't even see a light gap there. It's very, very close, okay? So the idea is I'm going to heat this thing up. Have to have a little patience here. Heat it up and see what happens. So that's going to take a second, but it's worth it. And no doubt that flame is hot. So it satisfies the sensation, hot and cold there. So it's already getting stuck. So it is expanding. And there it is. I can no longer push it through. And now if I just look at it or put a ruler up to it, I'm probably not going to notice something unless I use some calipers. But it has expanded. It no longer goes through. The other version of this, turn that off for a moment. The other version of this is a ring where the ball will not pass through. And the idea is to see what happens if I heat this up. There seem to be two possibilities. It could expand the way an inner tube expands, and the inner part would get smaller and the outer part would get larger. Okay, so we're just going to see what happens. Shouldn't take too long, but close, but not quite. Let's do a little more. Here we go. So pass through, pass back out. So that's thermal expansion, just a phenomenon that goes along with hot and cold. So thermal expansion. I wrote then, but I may as well replace that with thermal right here. Thermal expansion. Okay. Now here's an interesting phenomenon. This is metal, and the difference we see a little bit difference in color here. That side's more copper looking, and this side, although tarnished, is more silvery. And I apply some heat, and it bends. So it bends. This is called a bimetallic strip. What we have here is two metals that are fused. They're very thin, they're fused, but one side expands more than the other and pushes it into a curve. Okay, so we have that also as a thermal expansion. So ball and ring, and then the bimetallic strip. Ball ring, got the bimetallic strip, and I'll do a little picture of it here. This is kind of interesting. So you get that bimetallic strip, it was like that. You apply heat, apply a flame, and it bends to there. Let's do that dotted. And what I can show you later this semester is that if I were to put that into a very, very cold liquid nitrogen, it will actually bend in the opposite direction. And now we actually have constructed a thermometer, because we just mount it to something. We'd have a scale here, and this would be room, and this would be flame, and this over here would be liquid nitrogen. So to speak. So there we have, from these, first of all, hot and cold, then we have thermal expansion. We go to a thermometer. And if we're clever about it, we could make some gradations here. And so this is already a thermometer, but the next step here would be to invent a temperature scale. So thermometer, I like to number things here. So are we numbering? Let's go ahead and we'd have the thermal expansion, and then this would be 4, this would be 5 and 6. I'll just write next. Temperature scales. Temperature scales. Okay. So now our temperature scales we're going to have to tie to some phenomena as well. And I brought another type of thermometer, more standard one there. It's got a liquid inside. This is outside of the resolution, I'm sure, but it's got a liquid inside and a bulb at the bottom. And actually, if I just apply heat here, this has been in room temperature all day, and I can see in real time that this little column inside is actually moving up. Okay? I can see it, you can't. Okay, but let that be said. So there's another type of thermometer. So let's go ahead and use that idea to talk about temperature scales. Yeah. So I've got two boards here. When I'm doing demonstrations on the table, I just use one. If it's all theory, then we have both boards. So this venue is actually pretty good. All right. So we're tying in the temperature scales and the phenomena. So let's go ahead and draw a couple of thermometers here. There it is, it's a capillary, and I'll draw a second one. And they've got a little red down here, liquid in there. That liquid expands with the thermal expansion, and so we get different height depending. Okay, so thermal expansion, the temperature scales, we just have to tie them to some phenomena. So what we can do is say ice melts, say that down here, and up here we can say water boils, and I can do both of those experiments in here. I can have ice water in here, and I can bring it to a boil and measure the height of the column in each case. But then it's just a matter of convention whether I am in the Fahrenheit scale or the Celsius scale. Okay. If I'm in the Fahrenheit scale, apparently I've got 212 and 32 by convention. And if I'm in the Celsius scale, I just have 0 and 100. And you see, you could do this, and then you draw some scales here. You could do this arbitrarily, but these are the two standard ones that we're concerned with. Now, if you want the conversion between these two, and you assume a linear relation here, then you can do the following. You could create a graph. You could say you've got degrees Fahrenheit here and degrees Celsius here. So we'll call this our 0 and our 100. We call this our 32 and our 212. And we're looking to find the equation of this straight line. If we can find the equation of this straight line, that'll be degrees Fahrenheit in terms of degrees Celsius. And we can do the opposite as well. So what do we have? We have delta T degrees Fahrenheit divided by delta T degrees Celsius is 212 minus 32, which is 180, divided by 100, 18/10, which is 9/5. Okay, so that's the slope right there. And we can say that T degrees Fahrenheit is equal to the intercept, which is 32, plus 9/5 T degrees Celsius. So that's how you get the conversion factor. Of course, now you can just look things up and do the conversions. But, okay, that's kind of interesting. And you can, of course, invert this. T degrees Celsius equals 5/9 times T degrees Fahrenheit minus 32. Okay, you just invert that. So those are your temperature conversions. Let's go ahead and write down temperature conversions. So I have a couple of basic problems on homework that'll be dealing with this. Okay. The linear relation. Okay, good. So where are we going to go next? Scales. Right here we have the phenomena, and we could have done it with our apparatus right here. Okay. So next I want to talk about this device right here. Where I'm headed now is, we have Fahrenheit and Celsius, and you've probably heard of the Kelvin scale. So we want to motivate the Kelvin scale phenomenologically as well. So this is not, this is a mock-up of a constant volume gas thermometer. It's not exactly that, but it's a nice visual, okay? And I'll kind of extrapolate from this and draw a picture. We're headed for the Kelvin scale, but right now we're going to talk about the gas thermometer and the constant volume gas thermometer. So let's see. I'll erase this. So let's have a look at that device here. So what we have here is a beaker, and just air inside, connected with this hose to this bulb with the red fluid, goes up there, and it's open to the atmospheric pressure. Okay. So the atmospheric pressure is what we have all the way here on down to there. Now, let's go ahead and apply some heat. I could actually hold this in my hand, but if I'm in a hurry, I'll just use this torch here, apply a little heat. Okay, proof of concept. The column of red fluid went up this high, now it's retreating again. Okay, so I don't have to repeat that. We did see that for a certain temperature, we had a certain height of a column there. And we can already discuss that there's a gas in here, the gas expands, the pressure increases. You get pressure there. When this water column's up to here, the atmospheric pressure on top, and the pressure in this bulb is the atmospheric pressure plus some certain height of the column, okay? So we're measuring pressure on the one hand and temperature on the other. So if we were systematically to do this, we could do the old ice bucket, and then we'd have a certain height of a column, and we'd boil the water and have another height of a column. And we could do this experiment with different gases. Right here, of course, it's just air, but we could put in, nitrogen, carbon dioxide, etc., oxygen, so forth. So that's the idea of the gas thermometer. The constant volume aspect is not being shown here, but I'll discuss that too. So I'm just going to draw constant volume, or write constant volume gas thermometer. And let's go ahead and do this picture like this. So here's this beaker, got some fluid in it. Let's say we have a bulb in there with some gas. We're going over to another reservoir here. We're going to come out with a flexible hose, which I'll do like that, and then into a column that's open to the atmosphere at the top there. Okay. So let's go ahead and call this our red fluid. Say the column goes up to here. Okay. So what we have is a height of that column of red fluid. Since it's open to the atmosphere, we can write atmospheric pressure up here, and then we can even say P is equal to atmospheric pressure plus rho GH. You guys had that in fluids last semester, right? Height of the column. So that is the pressure, and what pressure is that? That's the pressure in here. So I'm going to go ahead and draw these blue dots. That's the pressure in this gas here. Now the constant volume aspect of this device is that I can raise and lower this, because what I have to keep constant is this level here. So this level here, this one that goes to there, is what has to be kept constant so that the volume of this thermometer is constant. That's the idea. Okay. So hold, so I'll just put here, hold this level constant. Hold. And you do that by maneuvering this thing up here on the right. Hold this level constant. And that's what constant means up here. Okay, so there's the device. And there's a gas in here. Oh, I'll draw, there's a thermometer here. I'll just draw degrees Celsius. So there's the device, and we can control the temperature over here, measure the height here, convert it to pressure. Okay. So let's go ahead and do a graph of what these experiments result in. So the result of these types of experiments is pressure versus temperature. Graph. Wait a minute. Do this again. We need some room on the left side of this graph. Some people may know where we're headed with this. So there's temperature in degrees Celsius. There's pressure in some units. Could be atmospheres, could be Pascal. That's fine. And here we'll do 0 and 100. And then we'll set up some data points. So that's one gas. We'll do a different gas, and we'll get some other data points. And they tend to be linear. But the extrapolation of these two curves, these two sets of data, end up miraculously at the same point, and the second, the third, or fourth gas will do the same thing. So there's an extrapolated point, and it turns out to be T equals negative 273 degrees Celsius. And under these circumstances, we have something real interesting. If we were to choose this as our zero, then we would have a straight line graph, and pressure would be directly proportional to temperature. Okay. And that's a nice thing. And other reasons lead to the idea that this is the coldest possible temperature, coldest temperature whatsoever. If you have air and CO2 and stuff, they're actually going to liquefy long before you get down to minus 273. Okay. But yeah, so this is absolute zero, or absolute zero, And the temperature scale where this is this coldest temperature, where this is 0, is called the absolute temperature scale or the Kelvin temperature scale. So Kelvin scale, we'll say T sub K for Kelvin is equal to T sub degrees Celsius. We share the same scale increment, plus 273. So that's our third temperature scale. And good, I'll put this in blocks. And the last thing we want to do is come back to the relation of all these things to mechanics. Remember, I started off with the little list here and I had kilograms, meters, and seconds. So what's the relation of thermal physics? Now we've had sensations, we have thermal expansion, and then we have this gas thermometer. What's the relation to mechanics? So that's going to be the next thing. The relation to mechanics is twofold. The very fact that, I applied a torch on this side and I raised a column of fluid on this side. The raising of a column of fluid means that the center of mass of this fluid was raised up. That means work was done. So work is a mechanical concept, mass times gravity times y. So already there we see that we applied thermal energy here, or we applied heat, we applied flame, and we got work out of here. So for that reason, we already know that we're talking about mechanical work. The other thing is, and this is really key, we have to have the idea that there are atoms. The idea that there are tiny constituents of matter here comprising this gas, and that these constituents are moving around. That's a really powerful idea in physics. And at that point, these things have kinetic energy because they have a little tiny mass and they're moving. And if they collide with that surface, they have a higher pressure, they push down on that surface, do the work as well. Okay. So we have the idea of work, but we also have the idea of kinetic energy at the atomic or molecular level. That's the connection to mechanics, and it means that everything we do in thermal physics will be able to reduce to the units, kilograms, meters, and seconds, just like we did mechanics. So in that sense, we never left mechanics, but we just made the connection to mechanics here again. Let me write that down, what I just said here. So that's our next topic. What is the connection to mechanics? Okay, so thermal physics, and mechanics. So everything you did last semester was mechanics, okay? And the first thing we have is, we have the work, simply the column, even in this very, very tiny column of fluid, if I increase the temperature of it by holding it and the column of fluid goes up, there's some work involved, okay? So there's a conversion of thermal to mechanical energy. So I'm just going to have that work. I'll just write thermometer. Thermometer fluid, let's just say that. And the second one, probably more crucial, we'll just refer to atomism. So atoms, molecules, for me they're all atoms, okay? I'm just going to use the word atoms. So kinetic energy of atoms, even though that mass is very small, kinetic energy 1/2 mv squared with collisions, collisions, etc. So those are mechanical properties. You guys studied collisions last semester, okay? kinetic energy, momentum, collisions, all that. We're going to do something next hour called the kinetic theory of gases, of the ideal gas, and then we'll actually calculate with energy and collisions and momentum and so forth. Okay. Good, so that's the connection to mechanics, and what that means is we're again dealing with kilograms, meters, and seconds, and any quantities that can be constructed from those. Right, energy has the units kilograms, meters squared per second squared. Okay, that's a good point. Let's see how we're doing time-wise. Since we have this pressure versus temperature from the constant volume gas thermometer, I'm going to take this discussion all the way to the ideal gas law. Okay, so I'll go ahead and erase this. So I'm just going to write here, so next, ideal gas law. The first thing is we have that Kelvin temperature scale, and we have temperature, actually we'll do the other way around. Pressure is proportional to temperature if we're measuring with the ideal, with the Kelvin scale, okay? Where 0 Kelvin is negative 273 Celsius. So we have pressure proportional to temperature. The second thing is we can use the same device, and if we hold temperature constant with the same or a similar device, we can find that pressure is inversely proportional to volume. So now we take the constant volume gas thermometer, except instead of holding the volume constant, we hold the temperature constant. Then we find pressure is proportional to 1 over volume. We put those two together, we have pressure times volume is proportional to temperature and equal to N K Boltzmann temperature. So this N would be the number of particles. This is a natural constant that I'll put up on the board in a minute, but you know, you can put parentheses around N K Boltzmann, and then you would have that proportional to temperature law right there. So this is how we get the ideal gas law. Put a box around that. And what I'm going to do next time is derive this on a molecular basis, namely using these assumptions, we're going to discuss this law. Right now it's phenomenological. It would be discovered by using an apparatus, you know, of the type that we're looking at right here. So that's the ideal gas law. And number of particles, Boltzmann constant. You can look that up. I'll put it on the board next time. Right now, this is just, would be in parentheses, would be the proportionality constant for that law right there. Good. So that's as far as we're going to get. I want to return now to what I'm going to assign for the homework and give you a little more background on thermal expansion. Here I just went through with the broad ideas, but we're going to have a little bit of formalism for the thermal expansion as well. So I'm going to go ahead and erase this, and I'll put the homework problems on the board, and then we'll have a look at them and see what we need in terms of formalism. So I have written down homework number 1. So we have chapter 17, and these I've actually sufficiently dealt with. Problem 32 and 35, some kind of conversion problems or column of fluid type of problem. Pressure and temperature problems right here. So those need no further discussion. Chapter 20, problem 26 and 27. And here, we need a little more thermal expansion formalism. So if you actually do systematic experiments with these metal objects, you can get the following law. The linear thermal expansion law, and that just means the linear dimensions expand. So even if I'm doing this ring here, and I showed that the way it expands is the whole thing expands, also the inside gets larger. So the linear dimensions of this would expand such that the opening radius expands as well. Okay, that's what we mean by linear. The length of this hoop expands, the radius expands as well. So there we have the change in length is equal to a proportionality constant L sub 0 change in temperature as measured in degrees Celsius. So we could also say L minus L0 is equal to alpha, no parentheses here, alpha L0 T minus T0. And traditionally, T0 is measured at room temperature. It's the best way to do your experiments, room temperature. So that's at 20 degrees Celsius. And these are degrees Celsius. But since the difference, of course, could also be Kelvin. And these are going to be meters. So alpha is a proportionality constant, or I should say it's a material constant. And you always want to get in the habit of asking what are the units of any new constant you're introduced to. Okay, so what are the units here? The left side is meters or length. This is also a length. This is degrees Celsius. Therefore, alpha is inverse degrees Celsius. So when you're asking for the units, you do the square bracket, and that's going to be 1 over degrees Celsius. I'm just going to write C text, and that will be in chapter 20. See the text for tables of values here. They're like, for a metal, it's something around 10 to the minus 6 or so. See text for values, different metals, different substances will have different linear coefficients of expansion. Okay, the whole table of values. You could look at the text and find them, and then you could go to your lecture notes and write down like 3 or 4 of them, and then you have a nice little set of values there. So yeah, look them up and insert a few of them into your text and into your notes. Let's see. Okay, so let's see what the problem set was going to ask us here. Got to move to chapter 20. Yeah, other topics in chapter 20 we'll do later, but this one is right off the bat. And I have there 26 and 27. So let's see what's going on here. Yes, this is a great one. Grandfather clock. Does a grandfather clock run faster or slower on a hot day? And the second one, so I'll get to the grandfather clock in a minute. The second problem here, this one is more basic. It's about heating something up so that you can fit it over something else. Okay, it's an interesting problem. In fact, this is actually a good time to discuss this. what can happen with these balls and rings, right? See, it doesn't pass through right now. If I heat this up, fit it over, and leave it in place, when it cools down, it's going to be more than snug, okay? Because it's going to shrink on it with enormous force. And then when you try to remove it, it's kind of hard because this, they'll both expand at the same time. How do you get it back off? So the type of problem where you heat something up till it barely fits, slide it over and let it shrink onto there, that's a very tight, it's almost like a weld, okay, very tight. So that's problem number 27. Problem 26, we're going to talk about a grandfather clock. And so this is something you must have had, hopefully had last semester, but the period of a pendulum, period T, T is equal to 2 pi, gotta pull this out of my, yeah, so it's 2 pi, period of a simple pendulum, 2 pi divided by omega, which means that goes length over G. Well, there's an interesting, important formula from mechanics. There's the period of the pendulum, and I'll draw the pendulum for you. It's just, it swings back and forth. The angle's what changes. It's got a mass here, and it's got a length of the pendulum. And the longer the pendulum is, the greater the period. And now imagine this is a grandfather clock pendulum, and it warms up, gets longer, period is longer, and that's the question that's being asked in problem number 26. Okay, so these are both great questions. I think you'll enjoy them. Remember, after you turn them in, ask me if you want to see any of these problems worked at the board. When we were doing normal lectures, when I have a class in front of me, what I do is I let the homework be turned in the following day, and then I'll just do any problem at the board. But can't do that, so we can do them a week later, though. Okay, we can do them after they've been turned in. Those are your homework problems, and I think we're good to go. Yes, we'll end the lecture right now. Enjoy these problems. Work on your notes. We're trying to get really good lecture notes all semester. Leave space in your notes. Everything I've done, you can study and learn how to do. We'll start getting more and more mathematical as the semester goes on. Good. See you guys next time.